Welcome to this third lecture in the series of lectures on textile printing. In this lecture, we are going to talk about textile printing, what exactly it is. Let's now look at the learning outcomes of this video. So in this lecture, we are going to talk about what is actually textile printing and what is it used for. We will then cover the main content of this lecture, which is to gain an in-depth understanding of the characteristics of textile substrates and how they influence the printing process.
Let's formally discuss about textile printing. We can compare printing with dyeing, as it was mentioned in your first lecture. Let's see on what points we can draw some comparisons. So as you probably have already understood by now, that printing is localized coloration of a textile or any other substrate. So we apply the color or the printing ink on a very specific area in order to create a design or a pattern on the substrate, on the fabric. In comparison, dyeing is the bulk coloration of a material, of a textile material, let's say. So you dip the entire bulk of the textile material into a dye solution and you expect all of it to be colored in the same shade. So that's called bulk coloration. In printing, usually we print multiple colors on a single fabric. In contrast, in dyeing, it's almost always a single color. So of course, because we are applying different colors on very specific areas of a fabric, we need to make sure that the boundaries of each color on the fabric are very well defined. This is of course not the case with dyeing. It's bulk coloration. In fact, you don't want any boundaries or you don't want any shade differences from one point to another on the fabric. So in order to achieve the boundary definition, in order to ensure that each color has sharp outlines or sharp boundaries, the colorant is applied onto the fabric in the form of a thick paste. Now this particular point is not valid for inkjet printing. We will look into this when we cover inkjet printing in detail. In contrast, in dyeing, the colorant is applied in the form of a solution, and the main objective there is to ensure that that solution is uniformly absorbed into the substrate in order to avoid any unnecessary shade variations on the fabric. As far as the end uses of a printed textile article are concerned, traditionally, textile printing is done, of course, for the purpose of decorating a fabric, for the aesthetic appeal of a fabric. However, there can be other applications of printing as well. Printing can be used to make a textile fabric functional. That is, printing can be used to impart some sort of functionality in the fabric. For example, in the form of electrical conductivity in the fabric. For example, in this image that you see here, you see the keys. These are printed onto a fabric, and it's kind of a keyboard inside that's printed onto a fabric. So that's possible because of the electrically conductive nature of the printing inks that are applied on this fabric. Now here you can see it's just a black fabric with the white keys on it. So you cannot say that this sort of printing has been done primarily for decorative purposes. The functionality can be in the form of thermal conductivity or thermal insulative properties. The functionality can be in the form of changing the appearance against a background. Now, this is a very specific case of textile printing. This is the military camouflage. And there can be other end use requirements as well that we aim to achieve with printing. Let's have a look at the difference in the two possible end use requirements of a printed article. That's the aesthetics and the functionality. So here you can see in this image the color selection, the motifs, that's all done to make sure that the printed fabric has a very strong visual appeal and it looks good to the eye. In contrast, when we talk about functionality, again considering the example of military camouflage, now these are also conventional colorants, and this is, let's say, a normal textile fabric, but simply The selection of the motifs that we are printing, the types of colorants that we are using, and the color combinations can actually change the end use requirements. So a military camouflage in that sense becomes a functional fabric because it affects the appearance of this fabric against a background. Now let's have a look at the characteristics of textile substrates in the context of printing. For this, you have to quickly recall the substrate properties that were discussed in the previous lecture. Those are surface roughness, absorbency, porosity, flexibility, and stability of the substrate that you are printing. There can be other substrate properties also, but these five are like the more important ones. We can actually consider these properties and we can compare different textile fabrics on the basis of these properties also. So here in this image, you can see a woven fabric, a knitted fabric, and a non-woven fabric. And very clearly from this image, perhaps most of you can appreciate the fact that these substrates will be expected to have remarkably different properties from one another in terms of these 5 points that are mentioned here. So these are, of course, very crucial to be considered when you want to print these substrates with. Let's have a look at surface roughness of textile substrates in a greater detail now. We know that yarns can be made from staple fibers or filaments, as you can see here in the image. We also know that in case of filament yarns, there is virtually no hairiness on the surface of the yarn. However, in case of staple yarns, there is generally a lot of hairiness on the yarn surface. In case of staple yarns, the yarn hairiness is further affected by the yarn properties. So the fiber length, the method of yarn production, like whether it's ring spinning or whether it's compact spinning, etc., the manufacturing process, the yarn manufacturing process, and the fiber properties determine the extent of hairiness on the yarn surface. So if a fabric is constructed using a filament yarn, you would expect its surface to be very smooth, as shown here in the image. And in case of a fabric that is woven or that is produced using a staple yarn, the surface hairiness is generally very high. So compare these two fabrics here. One of them is made of filament yarn, the other is made of staple yarn, and you can see that there's a huge difference as far as the surface roughness of these two is concerned. If we talk about woven fabrics, then the surface roughness is affected by the weave type as well. So there are different weaves. You have already studied these different weave structures. We have plain weave, we have twill weaves, etc. We have satin weaves. So let's say for a plain woven fabric, the surface appears to be like this under a microscope, and for a satin fabric, the surface appears to be like this. And again, from these images, you can quickly appreciate the difference in the surface smoothness or roughness, if you like. So in summary, if we talk about the surface roughness of different textile fabrics, the first point that we have to consider is whether the fabric is a woven fabric, a knitted fabric, or a non-woven fabric. Then if we are talking about a woven fabric, the weave type can also affect the surface smoothness. For the surface roughness of textile materials, the yarn properties also affect the final surface roughness of the substrate. And if I summarize that point again, then in case of filament yarns, you don't expect a lot of surface roughness, while in case of staple yarns, the fabric has generally very high surface roughness. Now let's talk about fabric absorbency. Absorbency of a fabric primarily depends on the fiber type. So we can have fibers that are hydrophilic in nature or hydrophobic in nature. On a hydrophilic fiber or on a hydrophilic textile, for example, cotton, a water-based ink will be very readily absorbed. In contrast, on a hydrophobic textile, let's say polyester or nylon, a water-based ink will tend to sit on the surface as shown here in the image. Now the image that I've used here is not that of an ink, it's actually water droplets sitting on the surface of the fabric, but you can relate this with ink as well. If the substrate is hydrophobic in nature and the ink is water-based, then it will tend to sit on the surface. Let's talk about fabric absorbency now. Optimal absorbency of a textile fabric is crucial not only for dyeing but for printing as well. As you can see in the image here, the droplet number 3 has not been absorbed to a greater degree into the fabric, while the droplet number 4 has absorbed to a greater degree into the fabric. In the context of printing, this is very important because it affects the fastness properties of the print, and it also affects the color brilliancy of the print. So if an ink droplet gets absorbed into the fabric too much, then probably the result would be dullness in the colors. So before printing, we set the absorbency, and that is done, of course, in the pre-treatment operations and primarily during bleaching. That's valid for hydrophilic textiles such as cotton. Think about this. Is too much absorbency good? Do you want a lot of print paste to get absorbed into the fabric? Let's talk about fabric porosity now. For fabric porosity, again, we have to talk about different fabric structures first. We have woven, knitted, and non-woven fabric structures. And straight away, you can see that the pore size or the pore structure for each of these types of constructions is different. So for a woven fabric, you would normally expect the pores to be of relatively smaller size in comparison to a knitted fabric. Now that depends on the thread count and etc. However, generally speaking, the pore size for a knitted fabric can be assumed to be slightly greater than the pore size for a woven fabric. And furthermore, you can note that the pores in a woven fabric are all almost equal in size. In comparison, for a non-woven fabric, you can see that the pores are not of a regular shape, regular profile. Some of the pores are very small, while the others are very large. So again, if we just focus on woven fabrics, then the porosity depends on the construction and the weave type. So here you can see different weaves. These are 4 different weaves, and the pores, the pore size, and the pore structure, and the distribution of pores over the entire structure of the fabric is different. That's because of the different weave type. Then comes the flexibility of textile substrates. As we discussed in the previous lecture, textile fabrics of almost all types are actually very flexible in comparison to other substrates. And that allows us to process textile fabrics in the form of rope or in open width form. And because of this, uh, we can actually pass a textile fabric over several rollers because it can easily flex over the rollers. This diagram here that you see at the bottom, this one, is that of, let's say, a washing tank of a bleaching machine. So this is a very common configuration that a fabric has to pass over a number of rollers in a processing machine, particularly when it is being processed in open width form. All of this is possible only because of the high flexibility of almost all textile structures. Stability is the next important characteristic of textile substrates that we need to consider. If the fabric structure is unstable, then it is of a great concern for us, particularly in the context of printing. Now, this is an important point to be discussed here, that this is not very crucial in case of dyeing, but for printing, if the fabric structure is unstable, then eventually there are chances that the print will also be distorted. The stability of a textile fabric depends on the fiber type. If the fiber is hydrophilic in nature, you will generally expect it to be more stable. If the uh, Then of course the stability depends on the fabric type, whether it's woven, knitted, or non-woven. Woven fabrics are generally considered to be more stable. In case of woven fabrics, different weaves can have different stability, and the overall stability of a fabric also depends on how the fabric is processed before printing. So if a lot of stresses are applied on the fabric during pre-treatment, let's say, then you would expect it to be dimensionally unstable by the time it's taken to the printing process. So let's now summarize the different textile substrate characteristics that we have discussed in the context of printing. The first one is surface roughness or unevenness. If a fabric has greater surface roughness or unevenness, then generally it would require more ink for proper coverage. The second textile substrate characteristic that we consider in printing is absorbency. If the absorbency of a textile substrate is too high, then a large portion of ink will be absorbed into the fabric bulk. This is actually a waste of ink, and as I've discussed in the previous slides, it could result in dullness of colors. Porosity is important to be considered, particularly for low GSM fabrics, because if a fabric has a very porous structure, then ink can possibly go through the fabric after it's deposited onto the substrate. And this can cause a staining on the backside of the fabric, or again, it could result in wastage of the ink. The fourth textile substrate characteristic that we discuss in the context of printing is flexibility. This is not a problem for us because textile fabrics of almost all different types are very flexible. Stability is one of the most critical requirements in a textile fabric that needs to be printed. If a fabric is not stable, then all sorts of problems can be observed after printing. The main problem is, of course, that of distortion of a design. So if the fabric structure becomes unstable after printing and the weft threads are, let's say, disturbed on original positions, then the print will also be distorted accordingly. We are going to look at this in greater detail in the following lectures. That's the end of the second part of first lecture. Thank you for listening to this lecture and see you in the next lecture.